All right, in this video, we're going to look at example 347. It's another static equilibrium problem, but this time not only do we have a hanging crate, it is connected to two springs from O to A and from O to B, and also a wire that goes from O to C. So it says determine the stretch in each of the two springs required to hold the 20 kilogram crate in the equilibrium position shown. Each spring has an unstretched length of 2 meters and a spring constant or stiffness of 300 newtons per meter. Okay, so let's just do some initial setup on this. So unfortunately, I probably made the diagram a little too small here, but I'm going to call this F. I'll just call it FC. It'll be in tension. And similarly, the springs, there's going to be FOA and FOB. And I'm just going to call this one, I mean, technically, I guess it's FG, so why not I'll call it FG for gravity, like there. So there's four forces. Actually, I should call this one FOC. My apologies there. And I'm assuming, and it should be the case, they're all in tension. So I've got good directions acting at point O for my forces. Okay, so once again, the first thing we want to do is write everything down in I hat, J hat, and K hat. Now, I think you can probably see here that at least three of them are going to be fairly easy to write. So, for instance, FG, that is just down in the negative Z direction. So it's going to be 0I plus 0J hat. Now, it's going to be downwards, and it's 20 kilograms. But remember, Fg is equal to mg. So this is going to be 20 times 9.81, which is going to be 196.2 newtons. And the direction is down in the negative z, so minus 196.2 newtons. Whoops, sorry, I'll write that K hat, and then I'll put the newtons on top. I think you can also see for my FOA, it's only along the negative y direction. So it's going to be 0I, and I'm just going to use minus FOA J hat. It's unknown the magnitude, and 0 K hat newtons. And similarly, FOB is just along the negative x. So this is going to be negative FOB plus 0 J hat plus 0 K hat newtons. Now, FOC is a little more complicated. We actually have to use a position vector. Notice here, and they do this to try and trick you as you're getting used to these 3D diagrams. Even though it looks like point C is probably somewhere in the back in the second quadrant there, notice that it goes up and then comes down here, and it is actually in the positive XY plane. And I'm hoping you can see from this that this position vector from O to C looks like it's going to be 6 meters along the I hat direction, and then 4 meters along the J hat, or the positive Y, and then it goes up 12 meters in the K hat direction. And so therefore, the overall magnitude of that, you're just going to add up 6 squared plus 4 squared plus 12 squared and take the square root. It actually turns out to be 14 meters on the dot there. So then you can write FOC, my bad. The vector will be the magnitude of it times the unit vector ROC divided by its magnitude here. I can write this as 6/14 of FOC I hat plus 4/14 FOC J hat plus 12/14. When you have nice fractions like this, it's not worth putting into decimal form at this point because you'll be able to maybe cancel some things out. I'm also not reducing any of the fractions, although you could here. Like, I'm just going to leave it as the 14ths for now, and we'll see about reducing it a little later on. because we now have these, and this is going to add up, because it's in static equilibrium, to 0I plus 0J, 0K. Now, I can also make one more simplification to help us out. First off, I'll write it up here. Notice, because FOA and FOB are springs, the magnitude of FOA can also be written as the spring constant times the stretch in spring A, and FOB can be written as the spring constant times the stretch in SB. So I'm just going to call it that. I'm just going to add up all the X components. I'm going to add up all the Y components. And I'm going to add up all the Z components. And so with that in mind, notice I'm going to get negative FOB, which I can write as negative K SB plus 6/14 FOC equals 0. I can do something similar for the Y components. This is going to be negative KSA in place of FOA plus 4/14 FOC equals 0. And finally, minus 196 point, I can't, 0.2 plus 12/14 FOC equals 0. Okay, so it's now an algebra problem. And you know what? While you're watching this video, notice that I can even start subbing in for K, because I know K is going to equal 300 Newton per meter. So what I could also do is just go to, just going to change this up. So this is negative and negative. There we go there. So now we only have three unknowns, SB, SA, and FOC. And now it's just an algebra problem. And I think you can see right off the bat there that equation 3, that's going to give me FOC. And that's going to be like 228.9 newtons. And then I can plug that back into equation 1 to get SB. And I can plug that into equation 2 to get SA. And I find that SA was, well, I ended up rounding it off a little earlier, but 0.218 meters, and SB was 0.327 meters. So the question asking, find the stretch in each of the two springs. So the final answer is to give us SA and SB, and this is going to be 0.218, and this was 0.327 meters there. And that is our final answer where we figured out the springs. Now you may think and look at this question and go, well, wait, why did they even give us the spring has an unstretched length of 2 meters? That's a red herring in this case, which means it really didn't matter to the problem. If I asked you to find what is the new length of each of those sides, you could add the stretch onto the 2 meters, but they were only asking for the stretch, which is the SA and SB. So they kind of gave you some extraneous information there that you didn't quite need. All right, so that is question 347. If you have any questions, as always, feel free to come and talk to me or send me an email. In the meantime, though, I hope you have a great rest of the day.